All right, I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you guide our work today. Help us to glorify you what we do. I just pray you help the students prepare for the test on Wednesday, just to be ready for whatever comes to them, Lord. In your name I pray. Amen. Oh, top hat. I almost forgot my top hat. Let's see here. So the internet's working again, right? Slowly. All right. I think you guys are section 3. Yep. And 5037. 5037 is the number. I won't call your name, but if you call your name, I'll give it back to you. Okay. Anybody else? Anybody else here who wants the quiz back? Didn't get it back yet? All right. So, see if I can fix this board. You guys got questions? So everybody's ready for test 2? 70% ready? So, questions? Let me shut this door. Should I do more completing the square? Anybody need to see that? Yes, no?
I could go for some long division.
Long division, all right.
Maybe one completing the square.
One completing the square? Okay, so how about this? X squared plus 16x plus 1. Let's look at completing the square and see what it tells us. Yeah? So if I look at y equals to this, then I can ask, I mean, this is the graph is what? It's a parabola, right? Where's its vertex? Where's its x-intercepts? Does it have x-intercepts? We can answer all these questions from completing the square. So we take half of 16, which is what? 8. You square that thing. Now to be fair, I have to subtract 8 squared, which is 64. All right, so that's it. That's completing the square. When the leading coefficient is 1, it's just that simple, right? And of course, if this coefficient is odd, then you get fractions and it's annoying, right? But anyway, this gives us what? X plus 8 squared minus 63. So from that, I can tell you where the vertex is. Where's the vertex? Where is the vertex? Can you guys tell me? Negative 8, very good. Negative 8 and minus 63. Yeah, we don't, it's only on the x that we do the flip-flopping. So the idea there, of course, is we're always thinking back to like our basic template, y equals to a times x minus h squared plus k, right? Has vertex h comma k. So we can compare to that, basic template, so to speak, right? Or you can think about it logically, right? Like the vertex is where this number is 0, right? Which is going to be the smallest value, I believe, that this can take, right? So if this is 0, the value of the quadratic is minus 63. Whenever this squared term is bigger than 0, you've got some number larger than minus 63, right? So that means that minus 63 is the smallest that it ever gets, right? That's the vertex of the thing, if you think about it. Okay, so that's where the vertex is. How about the x-intercepts? Does it have any? It does, right? Because when we complete the square, we got a minus, which means that we can actually factor it, right? Now, it doesn't factor pretty. We have to think about this. A little bit sneaky. So we have minus the square root of 63 squared. I don't always write out this step anymore because we've done it enough times that I sometimes skip I skip this step sometimes. I just go straight to here. X plus 8 plus the square root of 63. X plus 8 minus the square root of 63. So what I'm doing there is going back to day 1. One of the first things I told you is important is the difference of squares formula, right? So this is like a squared minus b squared, right? Where a is x plus 8, right? And this square root of 63 is my b. And if you have a squared minus b squared, you can factor that difference of squares formula as a plus b times a minus b. So I'm always just going back to that idea. Whenever I get a difference of squares, I can just break it up into a plus b times a minus b. And so this is a plus b, right? This pattern down here is a minus b. Yeah?
Where did you get the square root from?
Imagination. So the point is, if I'm going to apply the difference of squares, I need to think of 63 as being my b squared.
Oh, okay.
And so if I do that, then that means that b is either going to be plus or minus the square root of 63, but I might as well use the plus.
Yeah.
So, okay, anyway, you can pretty much ignore all of the writing I just did in red, right? That's just backstory, right? The writing I just did in red is to explain the factoring I wrote in black. That's all. You don't have to write that. That's just, think of those as the training wheels. You know, that's the logic that guided what I wrote in black. Now that we have what I wrote in black, this last step here, what does that tell us x-intercepts are? X-intercepts at x equals to minus 8 plus or minus the square root of 63, which is to say that the x-intercepts are actually minus 8 plus root 63, or rather minus root 63, comma 0, and minus 8 plus root 63, comma 0. So the graph of this thing, if we wanted to complete the thought, there's one, like minus 8, here's my minus 8, you know. And my vertex is minus 8, comma minus 63. I guess I'll just draw it here for the sake of discussion. And then, you know, I've got something like one x-intercept here, because the square root of 63 isn't quite 8. 7.5-ish, 6 or something like that. So this is still a little bit negative, right? A little bit negative. And same side on the other over here. You got that. What's the y-intercept of this thing? It's at 1, right? Is that here-ish? I don't know. So the graph looks something kind of sort of like this with the scale I've chosen. If that makes sense. Here's the vertex. It was, what was it? Minus 8, minus 63. My x-intercepts are minus 8 plus square root of 63, minus 8 minus the square root of 63. And I suppose I should label my axes, right? Here's y, here's x. And we're looking at y equals to x squared plus 16x plus 1. is good? Yeah. Well, how would we get no x-intercept? So how would that happen? Like, what if we had this example? Y equals to x squared, let's say minus 20x plus 200.
What was the question?
Would this have x-intercepts? Where's the vertex? Can you factor it? Can you factor it over the complex numbers? I don't think we can factor this one over the reals. Let me show you why. See, if I complete the square here, x minus 10 squared, right? Then I've added 100, so to be fair, I have to subtract 100, right? So I subtract 100. I still got my plus 200, so what do we got? X minus 10 squared, right? Plus 100. So this is prime, right? We can't do that difference of squares trick we did on the last one without introducing complex numbers. The only way I can factor that is to introduce complex numbers. Now, what's the vertex for this one?
10,
10 comma 100, very good. No x-intercepts, right? So if I graph this thing, what's it look like? Like, let's say here-ish, 10, 100. And then up here at twice as high, you've got another point. The y-intercept is at 200, right? And yeah, it's definitely a parabola. And it as I've made my graph here, it's something kind of sort of like this. So that's at 200. How do I know that? Sorry. How do I know that the y-intercept is at 200 here? It's nothing terribly profound. It's just that 200 is the constant term, right? If I put x equal to 0, I get 200 from that formula. Can you guys factor this over the complex numbers? It is something you should be able to do at this point. I don't think everyone can do this in here yet. I would say this is one of those things that would distinguish like a high A student from a low A student, this particular thing I'm about to do. All right. But to factor over the complex numbers, what I do is I rewrite this as x minus 10 squared minus 10i squared. See, because 10i squared is equal to 10 squared times I squared, which is what? 10 squared times I squared is negative 100, right? So as you can see, plus 100 is the same as minus 10i squared. Now I can look at it as the difference of squares. And so what I have is I've got x minus 10 plus 10i, x minus 10 minus 10i. So this is how we factor over the complex numbers, right? So most of the time, I only ask you guys to factor over the real numbers, so I don't expect you to do this, all right? So I might ask about this like one time on one problem somewhere, yeah. But this is the trick. You just complete the square and convert the plus thing to minus the same number, minus the square root of the number times I squared, basically, just like that. Anyway, no x-intercepts because the zeros for this quadratic are complex. Now the zeros are still interesting. Notice that, so like this is equal to 0 when? So if I call this thing f of x, right? We have f of 10 plus or minus 10i equals to 0, right? So this quadratic has a complex 0 of 10 plus 10i, or 10 minus 10i if you want to look at it. corresponding to the fact that this is a prime polynomial. This one has alpha equals to 10 and beta equals to 10 in the language of my complex zeros theorem, you know? So, what's the significance of alpha for the complex zero? It's where? It's exactly where the vertex is, right? See, because the vertex is at x equals to 10, like 10 is equal to the alpha in the complex root. That always happens. Okay, anyway, enough about that. Somebody wanted me to do a, what was it? Long division? Should we get to that? Can I erase? Okay. Okay, so let's try out x to the fourth plus 3x squared minus 2x plus 1. And we'll divide into that, let's say, x squared plus 3x plus 2. All right, let's see how this goes. So what do I start with? How do I get x to the fourth from this divisor? I'm going to multiply by what? X squared, right. So I'll put x squared here. And then I multiply this x squared by this and put it down here. So I get x to the fourth. X squared times 3x is 3x cubed, yeah? Plus 2x squared. All right. Now some of you have been taught to pad things with zeros, and like what I've written doesn't adhere to your formatting standards, right? You got to be careful that we only add like things, right? We can't add different powers of x. You can only combine like terms. X cubed and x squared are not like terms, right? So got to be careful when I do the subtraction. The x to the fourths cancel, right? However, x cubed, what happens with the x cubed? Nothing, right? There's nothing up here in terms of cube, right? So I've got a minus, that's the leading term actually, minus 3x cubed. Then look, I've got 3 minus 2, which gives me plus x squared. Then minus 2x plus 1, all right? Great, now the question is, how do I get minus 3x cubed from this? Multiply this by what to get minus 3x cubed? 3x, but not 3x, but minus 3x, right? But yeah, minus 3x cubed. And then I get minus 9x. I'll write it over here. Yeah. Oh, I'm an idiot. Minus 9x squared. I'm a dummy. This times this gives me minus 9x squared. And then I get what? Minus 6x, yeah. Now I have to be careful to distribute that minus, right? And I think I told you guys before, as you're looking at the handout I gave you on long division, beware that that minus is automatically distributed through in the calculations that I shared with you guys. Right? But I always like put parentheses and factor it out like this just to emphasize that that minus has to propagate through all of these, right? And all right, so what we got? These guys cancel. 1 minus a minus 9 is 10. So we get 10x squared. And this gives us plus 4x plus 1, right? So then what? How do we get 10x squared from this? Well, that is plus 10, right? So I do plus 10. That gives me 10x squared plus 30x plus 20. I subtract that, yeah? And what's that give me? That gives me minus 26x minus 19. And at this point, we're done in terms of like the long division, because long division stops here because the degree of the remainder, right? The degree is what? Degree 1. What's our divisor? Degree 2, right? Once this has smaller degree than that, you're done. All right, so what all this means? This means that x to the fourth plus 3x squared minus 2x plus 1 divided by x squared plus 3x plus 2 is equal to x squared minus 3x plus 10 minus 26x plus 19. I pulled the minus out over x squared plus 3x plus 2, right? That's what this long division tells us. This is how we can rewrite this quartic over this quadratic as a quadratic plus a proper rational function where we have degree 1 over degree 2 like that. You can also take this equation that we had at the end and you can multiply it by the denominator. What does that show you? That shows you that you can't really factor out x squared plus 3x plus 2 from this quartic, can you? Because what you end up with is this, right? So if you were going to try to factor out, if you're going to try to factor out x squared plus 3x plus 2, the lesson we learned from this is it doesn't quite work out, does it? Because this is as basic. What the long division tells you is the closest thing it is to factoring. Actually, like this is as close as it gets. But this term right over here, we can't somehow absorb that into a multiple of x squared plus 3x plus 2. Like there's no way to fix this. It does not factor, right? What this shows, if the remainder is non-zero, in summary, if the remainder is non-zero, then the divisor is not a factor of the polynomial you're dividing it into. Should we work another? I think we should work another, yeah? Let's work one that's a little bit more, that's a little bit quicker, but a little bit weirder. I'm not sure it's weirder, but here it is. Suppose we've got x to the fourth just a second, I need to, don't look at me. All right, so suppose we've got 2x to the fourth plus 3x cubed plus 4x plus 6. All right, and we're going to divide x cubed plus 2 into that and see if it factors. To erase the evidence. Here's the interesting thing about long division. The higher the power you're dividing in, the easier it is. Because well, let's see how that goes. So basically there are less steps. If I divide a cube into a quartic power, how do I get x cubed from 2x to the, how do I get a 2x to the fourth multiplying something by this? 2x, right. So I just put 2x there. And I multiply 2x by this, I get 2x to the fourth plus, well, apparently 4x, yeah? And we subtract these, what happens? These guys cancel, and we're left with 3x cubed plus 6, right? Then what do I do? How do I get 3x cubed plus 6? Multiply by 3, right. So I just do 2x plus, next up, 3, right? That gives me 3x cubed. 3 times 2 is 6. Hey, check that out. 0. The remainder is 0. What does this mean? This means that x cubed... Whoa. That means that x cubed plus 2 is in fact a factor, right? So what's this tell us? This tells us that 2x to the fourth plus 3x cubed plus 4x plus 6 is in fact equal to x cubed plus 2 times 2x plus 3. Is this completely factored? Well, no, but it's partly factored, right? I mean, this long division showed us how to extract that x cubed plus 2 factor from the fourth order one, right? Now, you could have seen that by factoring by grouping if you were really like with it, you know? Do you see that? Can you see this by factoring by grouping? Like, yeah, I mean, maybe you can, right? If you look at this, you've got yourself 2x times x cubed plus 2, right? That gives you this term and that term, and then these two plus 3 times x cubed plus 2, right? But the thing is, the factoring by grouping, you have to see it, right? Do you see it? I mean, this is a little bit disingenuous on my part because I told us to divide by x cubed plus 2, right? Which kind of begs the question, how do you know to divide by x cubed plus 2? Well, usually your college algebra teacher tells you to do it, is the answer to that. It's not a terribly interesting answer, but it is the answer nonetheless. My question remains to you, though, can we factor this further? What do you think? Let me get rid of this pesky factoring by grouping here. Can you factor, I mean, this we're done, right? 2x plus 3, that's pretty much done. I mean, you could factor the 2 out if you want, right? Factor 2 out of this, what happens? We can factor 2 times x plus 3 halves, right? So we could do that. I'll put it first, you know? If I do that, then you can immediately see that the 0 is what? Minus 3 halves, right? Like it would be 0 if I put in minus 3 halves. My question to you, though, is can you factor x cubed plus 2? Now here you have to go back, all right? Here's a walk down memory lane for you. And I don't think we've done this anytime recently, but just for, you know, for the sake of discussion, remember we had this formula, a cubed plus b cubed? What was it? It was a plus b, a squared minus ab plus b squared, yeah?
Wouldn't it like be complex?
Yes and no. So what I'm saying here is you could think of a as being x and b as being like the cube root of 2. And if you do that, then you've got x cubed plus the cube root of 2 cubed, which then if I use the a cubed plus b cubed special form trinomial thing there, it factors like this. Now this is the kind of thing, you know, to be honest, guys, I would be very impressed if you did this. So, but I'm just including it for fun, really. You're like, this doesn't seem like fun. Fine. For completeness, then. Now, going back to your question, is it complex? Well, this term over here is, in fact, complex. That one is prime. If you wanted to factor that, you need complex numbers. But now we're getting definitely beyond standard college algebra here in terms of difficulty. I mean, this is right on the edge of anything I would ever even consider putting on a test in here. Like, this is a high A versus A plus kind of stuff in here. This is not where this test is going to go Wednesday. So let me stop with it. I asked a question, could we factor it? It led me to say this thing, you know, that's all. But other questions? One of the other classes asked an interesting question. They asked, can you find the formula for a rational function given the graph? Right? We have done the opposite, right? I gave you a formula, you made the graph. Can I give you a graph and you make the formula for a rational function? Like, if you can do that, that means you understand pretty well, right? Let's try it out, see if you guys can do it. So let's see here. What I think I did in the other one was something kind of, sort of like, let's see here. So I'll put this one over here at like 6, and I'll put this at -4. All right, and I'm going to put an x-intercept here at like, I don't know, 2. Okay. And I'm going to suppose the graph looks something like this. Volcano here crosses through the axis here, and then goes down like so. And then it comes back over here like that. Right? So if you wanted to make something that looked kind of sort of like that, perhaps without my stupid wobbling here for my indecision in the graphing, could you give me the formula for something that would look like that? What if I pin us down a little bit more? I say, oh, you want to give me a y-intercept? Like, so suppose the y-intercept is 1, right? That should be enough to fix the graph, I think. Let's try it out. So you guys help me out. I think the formula we want, we're looking at the graph, y equals f of x. All right, let's build it. So this volcano, what do we need to make that happen? We need something in the denominator to be 0, right? We need an x plus 4. We better square it, right? Because it's got to be, you know, staying plus to plus as we go across the sign chart there. So we need an even number of x plus 4s, right? How do I get that vertical asymptote over here? I want a division by what? I want a division by x minus 6, right? X minus 6 is going to make us get an infinity there, in the sense that we're going to go from minus to plus, or plus to minus, right? If we just, whoa, well, that was funny. It's like, I guess it just decided it's done enough. Huh, yeah, all right. So that x minus 6 should pick me up this vertical asymptote here, right? I want a crossing it too. What do? I put x minus 2 upstairs, right? Because that's going to give me this x-intercept here, right? And then so up to this point, I can get these features, right? And I can stretch the graph out or smush it, and it will still, like, if you think about this, if you multiply this formula by any number, it doesn't change where the x-intercept is, and it doesn't change where the vertical asymptotes are. If you vertically stretch a rational function's graph, it does not move the vertical asymptotes, and it does not move the x-intercepts. Now, vertical stretching will move other things and move y-intercept, right? So what I'm saying is there's a freedom here. You can put any number you like there. What number do we want to put there, though? We want f of 0 to be what? 1, right? So we have a times minus 2 over 0 plus 4 quantity squared times 0 minus 6. So I'm just plugging 0 into the formula. What's that give me? Looks like minus 2a over 16 times minus 16 times 6, which is, I believe that's minus 96, right? So what do I find? I find a is equal to 96 over 2. The minuses cancel, right? And that's, I think that's 48, right? So lo and behold, we can, this could be the graph of y equals to 48 times x minus 2 over x plus 4 squared times x minus 6, right? So if you think back to your quiz, right, one of the things I could do, one of the games I could play, would be at that first kind of question I asked you to play matching game on, maybe it could be a rational function, right? It could be a rational function where I'm not going to like, the first question on the quiz was meant to be a quick question, right? Like you're supposed to be able to do it somewhat quickly without like a lot of calculation, let's say. It's really more about just identification of things. So the point here is, the thing about the y-intercept, that requires calculation. That requires some careful thinking. But the other parts here, like the fact that you got a volcano and you've got a vertical asymptote, you've got a crossing, x-intercept, that those correspond to this formula, that should be something you should kind of be able to see without further calculation. Now, why would you understand that? I think you wouldn't understand that unless you've done a bunch of examples, right? If you've been paying attention, though, to like the 10, 15 examples of these we've done at this point, you should start to see the patterns that we find, right? Like volcanoes come from squares in the denominators, and just the vertical asymptotes with the crossings come from we have an odd factor down here. Now, the question in the other section asked me about, what about hole in the graph? Could you put a hole in the graph? What if I also wanted to have a hole in the graph, say here? How would you do that?
We'd run it through like the A downstairs because you have to cancel it out to have a
It's no, you just do this. You just put x here and here, and to be fussy, this is no longer f anymore. It's the reduced function. So, like for another rather silly example, suppose I have the cubic, which goes through minus 1, 1, and 2, right? So what would be the equation for this thing? If I wanted the equation like this. What's the equation for this cubic? And what if you want to put a hole over here at 3, 1, put a hole? Can you give me the equation for that polynomial? So I'll start us out. We do y equals to, some constant, x plus 1, x minus 1, x minus 2. That, if we pick the appropriate choice of A, would give us the cubic that we're looking at there, right? In fact, we could figure out what that is by, if you want this thing to go through 1, basically, when x is equal to 3, we just put that in, right? We got 1 is A times 4, 3 minus 1 is 2, 3 minus 2 is 1, right? So apparently I would just choose A equal to 1/8, right? So I can do y equals to 1/8, x plus 1, x minus 1, x minus 2. That would give me the cubic without the hole. How do I punch a hole through that 3, 1 without changing anything else? It's a very sneaky trick. It's just not that sneaky. Once you understand it, it's really stupid. You just take this formula and you multiply by x minus 1 over x minus 1. How does x minus 1 over x minus 1 work? What is this equal to? There's two cases, right? If x is not equal to 1, it's just 1, right? If x is not equal to 1, these just cancel and give you 1. What happens if x is equal to 1? If x is equal to 1, it does not exist. So multiplying a given formula by x minus 1 over x minus 1, all it does is it makes everything work the same way it always did everywhere else, and it makes the number 1 undefined for the formula. That means you're putting a hole in the graph and changing nothing else. And if you go back and look at all the holes in the graph that we've done, you can understand them in terms of taking the reduced function, what I called the reduced function, and punching a hole in its graph. You can always look at it from that perspective. Like you could view it constructively in this way if you wanted to. But anyway, no. Just in terms of example building, there it is. I mean, we focus mostly on the, here's f of x, graph it, that direction of the logic, right? We spent comparatively less time, here's a graph, how do you find a formula to make that graph, right? But understanding both, if you understand both, then you really have rounded out your conceptual basis for things in here, right? It's like, it's one thing to understand how to get to work from your house, right? But it's also important to understand how to get from your work back to your house. There are different problems. Each is important, especially when dinner's ready.
What does D and E mean?
Does not exist as a real number. If you were a philosophy major and you felt like arguing with me, you could be saying something like, if it doesn't exist, then how are we talking about it? So I obviously mean it doesn't exist as a real number. It does exist as some sort of concept in this mathematical framework, right? Because you can ask the question, did it exist? Don't think about these things. Just accept as a real number. Other questions?
Wait, I do have a question.
Uh-huh.
So like if the whole was at 3, 2, the x minus 1 would be x minus 2, x minus 2.
If the whole is what?
If you were just going to say like the whole in the third example,
Uh-huh.
3, 2, if it was 3,
Oh.
2, would the x plus 1 be, or x minus 1 be x minus 2?
If the whole was 3 comma, oh, did I put the whole at 3? Oh, good grief. I'm so sorry, guys. Why didn't you guys stop me? This is undefined. I want to undefine at x equals to 3. I put the whole at 1. That was dumb. That puts the whole over here. My bad.
So it would be 3x minus 1?
Yeah, that would put the whole here. If I want to put a whole over there, my bad. I'm sorry, guys. I got to put an x minus 3 over x minus 3. I'm so sorry. You guys should... Oh. Oh, I'm very sorry for that. That was just a stupid juxtaposition of numbers in my mind. It's the x that we want it to be undefined for. The y is just where the whole is. You know, x is in the domain. It just so happened that 1 is where the x-intercept was in this case. So you notice how that works here? You get x minus 1 times x minus 1, you get x minus 1 squared. And then you got an x minus 1 on the bottom. If you go back to the theorem that we talked about, all the different cases, this would be the case where you have more copies in the numerator than the denominator. And we said that in that case, the hole in the graph was on the x-axis, which is exactly what this example has.
So the whole of 3, 1 is at x minus 1 over x minus 1 and x minus 1.
The whole what?
So like the whole for the 3, 1 is those two things that are divided.
The whole at 3, the reason there's a hole at 3, 1 is because I put the x minus 3 over x minus 3.
So that's the whole, not the x minus 1.
Right, this is putting the whole, over here. So you guys are all solid on the complex zeros theorem now, because we had some trouble with that on the quiz, right? So if you didn't understand the complex zeros theorem, it's important to take a step back and make sure you've got that on your formula sheet and you know how to do it, right? We did that a little bit earlier today for the quadratic, but anyway. See you guys Wednesday.